Hello, and thank you for watching this presentation on sustainable mining practices. This particular talk is about the geochemical considerations, that is, mine waste chemical composition, in mine waste management for sustainable operations and closure. Both myself, Valerie Bertrand, and my colleague, Kristen Salzsauler, will be talking you through the presentation. We extend our thank you as well to 2020 Northwest Territories and Nunavut Geoscience Symposium for this opportunity to present on the subject. So talking now is Valerie Bertrand. I hail from the Ottawa office of Golder, where I'm an associate in our mining environment and water team. I have a master's in mining engineering and a bachelor's in geology. In my career of 25 plus years, my experience lies in geochemistry of mine wastes, water quality assessments, water management issues, and environmental assessments of all kinds in Canada and internationally. My technical specialty is in geochemistry, geology, groundwater, and surface water chemistry on a number of projects in Nunavut and Northwest Territories. Kristen?
My name is Kristen Salzsauler, and I'm a geochemist in Golder's Vancouver office. I have a bachelor degree in geology and a master's degree in environmental geochemistry. And in my 16 years of experience working on geochemical assessments, I have applied the understanding of the geochemical characterization of materials to the development of mine waste management alternatives in the context of water management, waste management, and enclosure management. And I am also the leader of Golder's internal geochemistry technical community, which allows for collaboration between geochemists that work together on projects around the world.
Thank you. Today this talk will go over the following items. So what are the environmental risks associated with mine waste? What are we referring to in terms of sustainable mine waste management? We'll share our experience on northern specific issues that are a challenge to mine waste and water management. We'll provide examples of uncontrolled risks, what these can lead to. We'll present the various steps in the wheel to integrated mine waste management. Following that, Kristen will present key success elements and provide examples of real-life examples of implemented strategies for sustainable mining.
Thanks, Valerie. Mineral deposits contain sulfide minerals that, when exposed to air and water, oxidize and release acidity, sulfate, and metals that can contaminate local contact water. Even after the ore minerals are removed from rock and concentrated, some sulfide minerals will remain in the waste rock and the resulting tailings. Once these sulfide minerals are exposed and oxidation reactions begin, the process is difficult to stop, and control measures are complex and expensive. Furthermore, these measures may be required for a significant period of time. Identifying geochemical risks at the onset of mining allows for the development of management criteria, monitoring plans, and adaptive management criteria to achieve the environmental, social, and financial sustainability of an operation. Next slide, Val. The goals of sustainable mine waste management are threefold. First, to identify and manage risks at every stage of the mine life, to develop site and risk-specific designs that are flexible for changing conditions. Second, to optimize resource use, and in this context, we're considering both rock and water a resource. For example, cost reductions can be achieved by reusing geochemically suitable mine waste for construction, or optimizing the water management plan to reduce treatment costs. And lastly, to operate with the end in mind, using adaptable approaches that achieve and facilitate effective closure. The end point of this approach is to achieve the environmental, social, and financial sustainability of a mine operation.
For northern specific, there are some northern specific issues that need to be addressed. Permafrost aggradation in rock piles and tailings make rehandling much more challenging than in southern latitudes. Much more effort tends to be spent on this. Exposure of ground ice in open pit walls and ditches, for example, and for the it can lead to ground instability and soil erosion. Similarly, subpermafrost or below lakes where ground is not frozen, salinity of water can be an important issue to manage. Often a surprise, actually, to mine operators, both in the quantity of water and its quality. Climate, of course, is a barrier to shipping and construction. Water treatment plants and machinery used at site takes more planning and is more expensive to ship. This stresses really the need for controlling risks and avoiding surprises in the long term during operation as well. Ice buildup on ponds lock away water for use and for treatment as well. High spring flows make for the required flexibility in water storage and conveyance system. Let's not forget as well the pristine water quality and fragile ecosystems of the north mean that ground disturbances really need to be kept to a minimum to avoid generating contact water that might need treatment, for example, for suspended solids or other constituents, which really increase rehabilitation efforts. These clean lakes and rivers have really low assimilative capacity. Many lakes being very shallow, low volume, and can quickly show accumulated constituents from effluent discharge. This can lead to treatment objectives that can be substantially lower than in southern latitudes. So all of these specific issues do need to be addressed in their context. They need to be very site-specific in an overall sustainability of mine waste management. Some examples, the following are real examples of where the geochemistry of mine waste were either not considered fully, or the design did not address these risks, which then in the end required a lot more effort and go kind of against the sustainability aspect of trying to manage waste of waste management. These elements don't reflect necessarily one specific site. They're common to a number of projects. This particular example one is on the sometimes inadequate mine waste management planning that can go into a project. Here, the risk associated with geochemistry, that is the acidification and leaching potential from some mine waste, was unfortunately not carried through from design to construction. Construction cost control measures were put in place, eliminating that led to the elimination of some ponds and some of the water control infrastructure, such that all site waters actually got collected in the same pond without source segregation. Well, unfortunately, the geochemistry risks were realized, meaning that the materials started to leach compounds, contaminants, and the pond water got contaminated from these discrete sources and had to be retained in the pond prior to treatment. Unfortunately, there was no available treatment for this issue, and the volume of the pond was a bit too small to handle all this flow. So that resulted in, of course, the inability to retain or treat high volumes of contaminated water, and there had to be emergency discharge. In some instances where this happened, there's been a fine associated with this. So of course we could see the reasons for failure were lack of understanding and or communication of the risk issues, insufficient characterization of wastes, or lack of communication between the design and the construction team, mining teams working in silos. The design also, the lack of specificity to control the sources according to their risk was an issue. Management plans lacking flexibility and actionable alternatives were again another issue. So it's very important to integrate mine waste and water management planning to identify these risks before they occur and be flexible, have the ability to manage those risks at the beginning. So the consequences of this project, well, a few examples from different projects put together, is that sometimes these consequences can be that you have higher volume of contaminated water and more complex water treatment systems required because not all the issues were considered. That can lead to hasty, ineffective control measures, increased water treatment and closure costs, liability, and of course schedule delays, and ultimately amplified negative effects to the receiving environment. The other example is similar in a sense that they are still chemically reactive minerals mined and placed in a waste rock pile, but also used in dike construction. And geochemically, these materials started to seep, that started to oxidize and generate poor quality drainage during operation rather than predicted at end of mine life, because the material was not placed at its proper location. Water ponds, again, were not designed to retain and treat all this contaminated drainage. The material had to be rehandled, and costly control measures and unplanned emergency water capture and treatment systems had to be put in place. Again, high cost, surprise cost to the operation. The reason for failure was lack of understanding, again, of material properties. Not all the materials were characterized. For this particular place, this was a new mining zone, an expansion. The compositional variability of the material was not captured, such that, expected to behave just like the previous one? Well, not really. When it was used for construction, there came the surprise. The reactivity was underestimated, the reactivity of the new material. There was a deficient implementation of the design, similar to the previous case, where you have to have a system that is flexible to account for these changes. If you also have to have a system in place that can account for when the useful construction material comes on site, and have the ability to manage it. If you use inappropriate rock for construction, as in this particular case, and don't do the monitoring, you can't adapt your design. The consequences of this example are expensive emergency control measures that were implemented and which became unplanned operational costs for waste rehandling and water treatment. Of course, water treatment and closure costs are substantially higher than what could have been proper planning in material characterization, monitoring, and ongoing design adaptation during operation. So these examples lead us to these key success elements that are really needed when planning and executing, when planning and during execution to facilitate operation and closure of a mine. So the wheel starts at really understanding what your material is. The geochemical composition of your material. Characterize all and categorize all wastes. So the ore, the waste rock, the tailings, and develop mitigation measures for each. Example, what are you going to do with material that is leaching? Can you, maybe you submerge them or you cover, or perhaps the material is good enough and you don't need to do anything. You need to identify decision criteria, some, for example, cutoff values for each waste categories so that you are able to identify them and have a plan for each of the different categories of waste. During production, you need to implement the sampling plan for ongoing characterization. The first step, you have identified, well, what looks like, what the problem might look like, or what the solution might look like. In the second step, during production, you really need to validate what this problem or issue looks like. You need to set up plans for implementing sampling, and you need to allow for schedule, construction, and disposal of this material. You need to put this material back into the block model so that you're able to follow along and map out the issues as they arrive in order to be able to adapt your design. Facility design. You need to adapt it to what you've found, to your ongoing monitoring. You need plans to control the reactivity from the beginning by considering rock type, mining sequence, adaptability. And of course, you need to build to the design that you have. And if there's changes, then these changes need to be communicated. You need to identify the key performance criteria. How will I know whether the design I have actually works, actually meets the performance objectives? Well, you need to specify objectives, and you need to identify key performance criteria, such as a specific water quality or a specific chemistry of the wastes. And of course, performance monitoring. Analyze, collect data, allow for change management. Do put in your instrumentation. You start, and then all this information, your data analysis, your monitoring data for water quality, for permafrost degradation, for ground temperature, you need to feed those back to the original plan that you had, compare these new obtained data to the baseline, and make sure that you're in line for a program and a management plan that actually works for you and will achieve your goals. Kristen?
Thanks, Val. Controlling the geochemical risks associated with mine wastes begins with developing a robust and implementable mine waste management plan. This plan must be based on a thorough, site-specific geochemical understanding of the range of composition of the mine waste materials. And that plan is going to provide the basis for planning actionable alternatives for what to do with the mine waste. The plan needs to be developed in an integrated manner between different operations at a site, environment, operations, and closure teams to achieve common goals. And it's important that the plan is first trialed and then implemented early in the mine life, proven with monitoring data, and adapted as necessary based on monitoring results and feedback from the various project stakeholders. A proactive planning approach will ultimately reduce costs and liability associated with the reactive control measures. So let's walk through some examples of effective mine waste strategies that we've seen implemented at project sites. First and foremost, the geochemical characteristics of mine waste can be incorporated into a mine's resource block model, which then can be used as a tool for material use according to a geochemical classification. This allows for the development of mine waste management schedules that can be incorporated into facility designs. And during operations, this schedule can then be ultimately integrated into deposition plans in order to sequence material placement in a way that's best suited to its geochemical risk. Strategies that build on the classification and selective placement of mine waste will ultimately include adapting infrastructure design to material characteristics. For example, understanding the classification of a material and when it's available at a given time, and planning for the placement or encapsulation of reactive waste rock in the core of mine waste facilities is one way to minimize geochemical risk. These approaches tend to require a detailed instrumentation plan to test the functionality of the design, and in special regard to projects in the north, they require consideration of the unique impacts of the northern climate, including effects of adapted infrastructure designs on water management, reduced construction season, development and maintenance of permafrost zones, and the long-term potential of climate change impacts on the proposed design. Lastly, in our experience, the success of integrated mine waste strategies is a function of implementation and information sharing. Ongoing, regular monitoring of the mining infrastructure in which the material with a high geochemical risk is placed is critical. The construction plan, risks, and controls must be well understood by all stakeholders, and the results of monitoring need to be shared in a regular and timely manner to allow for reaction and adaptation. This type of information sharing should be considered with the same relevance as a safety meeting. The mine waste plan must have buy-in from stakeholders from each department in a mine operation, and continued communication is required to identify issues and discuss solutions that are required to mitigate risk and achieve environmental, social, and financial sustainability for the operation.
Thank you very much.
Thank you for attending our talk.